Mechanical duct and pipe systems modeling. When working with Autodesk Revit MEP, engineers are quickly thrown into a world of 3D thinking, where with traditional CAD the focus was primarily on schematic-based drawings with 2D symbols. The push to model more accurately where mechanical facilities are located is being required on more projects, thus the incentive to use Autodesk Revit MEP. MEP has intuitive 3D drawing tools modeling HVAC and piping systems. To demonstrate the ease of connecting ductwork between HVAC equipment, I first used the placeholder tool. The placeholder tools are designed specifically for schematic design and allow for single-line conceptual layout capabilities. This allows the engineer to lay out a very schematic design layout of where duct and piping is placed, without being concerned about exact sizing of systems. Select the placeholder duct and draw in some duct. This will automatically select the last duct system that you previously drew. Since the placeholders will not place all of the fittings or actual sized duct in the model, manipulating the single line geometry is easy as there are no connections made. A schematic layout is not only a 2D sketch, but also contains 3D relationships without connectors. Therefore, it is especially convenient to open a 3D view as we add the remaining duct placeholders. These placeholder tools allow engineers early design layout flexibility that previous versions of Autodesk Revit MEP did not allow, as the connectors and sizing are omitted until we are ready to convert these placeholder lines to actual ductwork with fittings. Although the placeholders don't have physical connectors and model geometry, there is still intelligent information associated to the system like required flow, size, and energy performance. I can select on a placeholder duct and view the information for the selected duct in the Properties palette. Autodesk Revit MEP now allows you to add tags to the elements in a 3D view. In order to do this, the 3D view must be locked. When I lock and save the orientation of the 3D view, I specify a new name for the view. I can add the tags in either open view. Additionally, I can select on the space that the terminals feed to determine if the area is getting the required airflow. Notice at this point, the supply airflow for this space is not being computed. This may be especially important for a design analysis workflow where we want to evaluate if our zone is supplying the correct amount of flow based on the energy analysis. Using Autodesk Revit MEP, I analyze the heat and cooling loads to calculate the space requirements. After the spaces are calculated, you can close that report. Selecting the space again, you can see that the calculated supply airflow has now been computed. Notice the actual supply airflow is more airflow than what is required in this room. To fix this, I select the 6 air terminals in the room and change the airflow so the total airflow for the space is closer to the calculated airflow value. Additionally, I changed the specified supply airflow for the space to match the calculated value, and I enter a specified return airflow value of 10% less than the supply airflow. I also changed the flow value of the return diffuser in the room and verify that the space properties reflect the change.
Once the correct flow is assigned to the air terminals, I can size the duct.
I select the entire duct system supplied by the heat pump and run the automatic duct sizing tool. Notice the tags reflect the new duct sizes.
Next, I examine the duct sizes and identify a problem. The main duct is smaller than the branches. The system is not closed and will require an end cap as well as some intermediate transitions along the main run to balance the system correctly. This will create the most efficient HVAC system. Next, I add the end cap. Then I resize the system using the same settings as before. Once the duct system is closed and resized, I observe the sizes to make sure that they are correct in accordance with good engineering practice. Next, I quickly select all the takeoffs in the view and change them to a standard round takeoff. Next, I select the desired locations for transition fittings in the main duct run. Then I resize the system using the same method and settings as before. I note that 2 transitions were added to the main in order to maintain equal friction flow characteristics in the main and branches.
I can add flex duct to the duct system using the Convert to Flex Duct tool. When I convert the ducts that connect the diffusers, you can see the changes in the 3D view. Next, I select the entire duct system I just created and copy it to the other 2 rooms of my building. Once the systems are copied to each room, you must check to make sure they are connected to the heat pumps. Since they are not, I simply delete the existing connector and then drag the duct to the connector on the heat pump to establish a connection. As you can see, the duct systems are now connected as desired. Although we did not show it in the demonstration, piping works similar to the duct. I can place the pipe using placeholder tools and then convert to actual piping with connectors using the Convert Placeholder geometry. It is important to be able to draw these schematic one-line representations and not be confined to actual geometry until sizing. You can utilize the interference detection using the placeholders to find collisions, even though the geometry is not shown.